Okay, I'm going to go ahead and get started. Can everybody hear me okay? We are in the third lecture of 4, so if you've been to all of them, we're over halfway done. Yay! Again, just to reiterate, all of these are being recorded and posted on our department website. They'll be there probably until we do this again next year, and I try to make changes every year based on feedback from you all. So it may be that you could come again next year for a refresher course or maybe see a little bit of new material based on your feedback from this year. So we've already talked about fundamentally what is statistics, what's the vocabulary behind statistics, how do we evaluate the quality of evidence based on the actual design and the purpose, the intent of the experiment. We talked briefly about power calculations and errors. Today we're going to get into hypothesis testing. Now I've already given you a brief introduction to the concept of hypothesis testing. It's actually a very difficult thing to truly understand. Now I have a PhD in statistics from a very good university. And I am quantitatively inclined, meaning I got A's in all my math courses. I tend to think like a mathematician or a statistician. When I took a stats class in my undergrad, I got out of that course with an A and understood essentially nothing that I did. So what I had in my back pocket was a cookbook. And that's, I think, what most people have in statistics. And when you follow a cookbook for doing something like hypothesis testing, but you don't understand why you're doing what you're doing or what you're getting from the method actually means, your chances of doing things incorrectly are astronomical. So if you don't understand hypothesis testing, if you really don't understand what that p-value means or why you're rejecting a hypothesis or the mechanistic process behind everything, that's okay. What I hope to do today is give you some brief insight into what you're actually doing. Where is that p-value coming from? Where does the confidence interval come from? When I get a test statistic like a T, where does it come from and what is it telling me? In English, not in numbers and Greek letters. And then I'm going to give you some actual applications. We're going to start off today with continuous data, which we very often summarize using means, because that's where most people start, is the t-test. So we'll start off with the t-test. We'll do 1 sample, 2 sample, and then we're going to branch off into more than 2 samples. If you have more than 2 samples, meaning you have, for instance, a design or an experiment where you're comparing 3 groups, and you're looking at the means of those 3 groups, it is not appropriate to do a bunch of t-tests. We won't talk about the details. I'll just say that it increases your chances of making errors, of finding results, finding significant results or significant differences when they don't actually exist. So it has to do with inflating error rates. What you use when you have more than 2 samples and you're interested in comparing the average response across those different groups, you use something called analysis of variance. It's just an extension of a t-test. So all the mechanics and the conceptual, the interpretation, all of that stuff that we're going to talk about and focus on for the t-test is the exact same for an analysis of variance. It's just that the test statistic is not a T. It's an F. So I'll make sure I reiterate that. Once we get through the sample means for 1 sample, 2 sample, more than 2 samples, then we're going to get into proportions. Proportions are interesting when we have categorical data like gender or response to treatment. Either they had a successful response or they failed. So like a yes-no, like a binary outcome, which is categorical. We'll talk about a couple of different scenarios that you could have when you have categorical data. It could be you have a single group and you just want to know what's the proportion of subjects in my sample, or my population actually, that fall into these different classifications. Or you could have 2 samples or 3 samples, treatment groups, and within each of those treatment groups you may have a response rate. And you're interested in seeing whether that response rate, that proportion of subjects who responded, is the same or different in some of those treatment groups. So there's different types of tests that we can use for that kind of categorical data. Next time, you'll notice on August 1st, it says hypothesis testing continued, is when we're going to get into linear regression, correlation, survival analysis, and if you have anything else that you'd like me to cover, there's my email address. If you email me today and say, you know, I would really like to see a non-parametric example, then I'll try to add in a non-parametric example next time. So I'm just basing this lecture on literally the feedback I got last year and the feedback of those of you who have already called me and talked to me about, well, could you show me something that I'm actually struggling with every day or very frequently throughout the year when I'm doing my own research. So please feel free to email me, and I will try to make time to modify or add in an example if the time allows. So before we dive into hypothesis testing, let's talk about some stuff. So here's where we're going to try to understand what we're doing before we go and do it. Hypothesis testing uses a sample, observed data, from a population of interest where the population is not observable because it's maybe too big, for instance, to make inferences about the population. In particular, about some characteristic of the population, like what's the mean response of this population if I apply this treatment. Statistics is the tool that provides us with the ability to draw inferences from the sample to the population that's unobserved. Here's an example that I'm going to use to facilitate thinking about hypothesis testing. There's a research problem, and I have the reference here. I'm using their summary statistics, but not necessarily their hypotheses. Many survivors of traumatic brain injury suffer from chronic cognitive impairment. What that really does is it affects their long-term quality of life. The issue that they're addressing in this paper is that survivors, even with similar injuries, tend to have cognitive outcomes that are all over the place. They vary greatly. So they're asking whether or not there are some other factors besides the type of injury that could have protective effects against cognitive impairment. The one that they investigate has to do with education, which they call lifetime intellectual enrichment, but it's really what they're measuring is number of years of education attainment. So suppose, based on these kinds of questions, that this is a new field of research for us. We're going to do a pilot study because we really don't know what cognitive impairment looks like. How do we measure it? What does that score actually reflect? We don't know in our population the breakdown of intellectual enrichment, educational attainment. So we're going to actually use a small study to estimate the cognitive status of TBI survivors in a couple of different categories. We're going to look at TBI survivors on the low end of the spectrum, which would be someone who has a high school education or less. We're going to look at the higher end of the lifetime intellectual enrichment scale, which is someone who has at least a graduate degree. And then eventually we're going to compare them to healthy controls, because that's what we would want to do in real life. So let's think about what we're doing here. The general population, this is everyone, not just TBI sufferers. The general population has some distribution of cognitive status. The score that we're using in this example is a score where 0 essentially means normal cognitive status. So if you're normal, theoretically you should have a 0. if you have impaired cognitive status, you have a decline in this score. So you're going to be somewhere over here. So it makes sense that in nature, cognitive status will have some average, which is normal, quote-unquote normal. You'll have some that are on the higher end of the spectrum, some that are on the lower end of the spectrum, and we can reasonably assume that the behavior of this score, which we'll call CS, is approximately normal. So on this figure, what I'm describing is the population, the general population. The x-axis is that score, our outcome measurement. If you're interested in more details about that, you can actually reference this paper. For those of you who study TBI, you may already know much more about this score than I do. The y-axis represents the relative likelihood of someone in this population having that value. So, for higher values of this function, we know that this value of cognitive status score is most likely. So the most likely value we're saying is going to be 0. And as we get further away from 0, either in the negative or positive direction, the chances of someone having that score greatly reduced. So everyone understand this graphic. It's fundamental that you understand how to interpret a probability distribution, which is what this is. Any questions? There's one thing about this distribution that's also important to talk about, and it's this parameter, which we call sigma. Sigma is just another Greek letter that statisticians like to use to indicate standard deviation. So we assume that this cognitive status score in the general population has an average of 0, but among the general population, it tends to vary by 1.5 standard deviations. So what does that mean? On a normal distribution, between plus and minus 2 standard deviations, we have approximately 95% of the population, right? So when we think about things clinically, if we look at an individual score and they're more than 2 standard deviations away from the average, what do we think about them? That they're abnormal, right? So everyone should fundamentally understand what a standard deviation tells us. It's just a distance, but it's a distance that reflects how spread out or varied or heterogeneous, for instance, our population is with respect to this outcome measure. So going out 2 standard deviations from 0, 1.5, 3.0, and in the opposite direction, minus 1.5, minus 3.0, I have approximately 95% of the general population. So if I randomly drew someone from this population, I would expect them to have a score definitely not beyond 3, but probably even within the range of minus 1.5 to 1.5, because it turns out there's something called the empirical rule for the normal distribution. About 65%, actually that's not accurate, it's about 68% of all subjects would fall in between plus or minus 1 standard deviation. So even there you're getting 2/3 of your population in between minus 1.5 and 1.5 on this scale. Now let's start the engine for hypothesis testing. What do we actually do when we want to investigate a question? We draw a sample from the population. So we've defined our population. In this case, let's just use the general population for now. I'm going to pull a sample of subjects from this population. My sample size in this case is only 10. But you can see here, here's my cognitive status score for all 10 of my subjects that I pulled. So I've got someone that's about a -2, someone that's about a -0.7. I've got several people who are positive. But notice, they're all between -3 and +3. If I take them, and I'm going to create a histogram. This is what we tend to do when we have continuous data. Drop those values down onto an axis that's the same axis as above, and plot the data. Is my sample normal? I don't know. I've only got 10 observations. I can't tell if it's normal. So that's an important point that we'll get to in a moment. When I'm interested in talking about a population average, I want to grab something from my sample that relates to that. So a sample average, for instance, would make sense when I'm trying to make inferences about a population average. So of my 10 subjects, I calculate the average. I'm sorry, you do. You're taking a sample. I'm going to take a sample in a minute. This is you. You take a sample, size 10. These are your 10 subjects' scores. You calculate your sample average, and you get an average cognitive status score of 0.137. Now, independently of you, I go out and I decide I'm going to investigate this problem too. So I'm going to collect 10 observations, or 10 subjects. I'm going to measure their 10 cognitive status scores. This is the histogram of that data. Just drop it down on a different axis, but the axis means the same. My sample mean is 0.346. Why is my estimate, this is what the sample mean is, why is my estimate of the population mean CS score different from yours? So in reality, let's assume that population distribution that we have at the top is true, that that's really what is there. In reality, the true mean score is 0. You took 10 subjects from that population and you got a mean score, a sample mean score, estimating that value of 0.137. I took also 10 subjects. Their sample mean score was 0.346. Why are they different? How many people are in the general population of the United States? I don't know. A lot, right? Millions? What are the chances that, let's say I'm in Lawrence, Kansas, and you're in Dallas, Texas. What are the chances that we're going to actually randomly select the same 10 people? In that case, I'm going to guess 0, right? Essentially 0. But even if we're in the same city, the chances of us having some overlap in our samples is very, very close to 0. So the answer to this question, why do estimates like sample means tend to vary from sample to sample, is because there's something called sampling variability. And in English, that's exactly what it is. My sample was different from your sample. The size was the same. They came from the same population. But because we only sampled 10, the chances of any overlap in those two samples is really small. So sampling variability is the issue here. We each individually only sampled 10 subjects from the population. The chances that my sample will consist of the same subjects as yours actually is a function of the size of my sample relative to the size of the population. So what do I mean by that? This is really what just happened, right? We had this huge population. I took a tiny, tiny picture of it, and you took a tiny, tiny picture of it. So there's lots of room for us to get truly independent samples where I have 10 different subjects than you. So the size of my sample, as it increases, we're actually increasing the chances that we could end up with some of the same subjects. I would argue this is still really small. If we have similar subjects in our two samples are statistically correlated, right? So it makes sense that my sample mean would be similar to your sample mean if of my 10 subjects, 3 of them were also in your sample. So I decrease the variability in our two sample means simply by increasing the sample size. if we took samples of size, we'd have to take really big samples to get this situation. Let's assume our population is not millions. Let's assume it's 1,000. And I'm taking 500 and you're taking 500 randomly. We're probably going to get some overlap, right? At some point, some of my subjects will be some of your subjects. The larger we get our samples relative to the size of the true population, the chances of us having almost identical samples is very, very high. In fact, we would be taking what's called a census if these red circles ended up matching the exact population. In that case, 100% of my subjects would be yours, and vice versa. So our sample means would be what? Exactly the same. There would be zero sampling variability. And why is that? Because we took a census. There's no uncertainty there. So that's not a statistic. That's a parameter. We looked actually at the parameter in that case. Any questions about sampling variability? Again, sampling variability is the reason why from sample to sample, even if they're the same size and from the same population, your statistics, your estimates, your confidence intervals, your p-values could end up fluctuating. And the amount they fluctuate is directly related to how large your sample is. That's why we like bigger sample sizes, because we tend to have better stability in what we're estimating. So let's take a step back after we've gone into that. So you took a sample, I took a sample, we saw there was some difference. Our samples were both of size 10. Let's suppose everyone in this room independently takes their own sample of size 10 from this population, where there's a mean of 0, a standard deviation of 1.5, and we think that 95% of the population should have a score between -3 and +3. So this was your sample mean. Here was my sample. I'm going to drop down my sample mean. Now I'm creating a histogram of sample means. Let's stop here. This is the population. This is a single sample, and that sample's mean. All I'm doing at the bottom is collecting everyone's sample mean, just dropping it down. The axis is the same. Notice it's still 0, -3, and 3. Okay? Here's a different sample, someone else's sample. In between the last slide and this slide, I actually took a couple more samples and dropped their means down. So now I've achieved 5 different experiments with 10 subjects. I've computed the sample mean, and I'm creating a histogram for each of the 5 samples. Is that clear? What if I did this 1,000 times? Oh, I just did it 1,000 times. That was fast. What is this histogram? That is 1,000 sample means. 1,000 times we sampled 10 subjects from this population, calculated the mean, and dropped it down. I actually have an applet. If you want to see and play with this, I'm not going to do it during class because I think it will take up too much time, but it will show you all 1,000 iterations, or 10,000, or 50, or 5. You just have to set the parameters of it. And you can actually watch the data drop down onto the green, calculate the mean, drop down to the blue, and you can see it happen in real time. So again, what is this thing? Population distribution of the CS score, right? That's the population that we're sampling from. What is this thing? It's a histogram of the data from one sample, right? It's my sample. And what is this thing? Thank you, thank you. Yes, a histogram of sample means, X bars, from 1,000 different samples drawn from that population. All the samples were size 10, 10 subjects each sample. So why? Who cares? Let's just take a look at this for a second. So if our population we're drawing from has an average of 0, what does the average of this histogram look like? The population average, right? So in English, what this means is, if I'm going to take a sample of size about 10 from the population where the real average value of the score is 0, then my chances of drawing a sample that has a sample mean similar to the population mean are pretty high, right? So the most likely values of sample means are values that are really close to the true mean. That's why we like the sample mean, because it tends from sample to sample to be very close to what's truly of interest. Again, I've got this app in my office if you want a copy of it. Without getting into the notation, the average of these sample means, so the mean of the means, the average of this histogram is negative 0.0025. 0, right? It's essentially 0. Yes, sir. Mm-hmm.
So after that many sampling in this study, would you reset 0 based on that?
Would you if it's negative 0.0025? On a cognitive status score, let's think about what the cognitive status score looks like. 95% of the population has a value between negative 3 and plus 3. About 2/3 has a value between minus 1.5 and 1.5. What's the difference intuitively between a 0 and a negative 0.0025? If I have a negative 0.0025 and you have a 0, what's the difference in our cognitive status? Nothing. The reason that this is not exactly 0 is because this is what we call empirical, meaning I'm using a statistical software to generate samples and compute their sample mean and then just get a histogram. So this is like not even the real sampling distribution. The sampling distribution is it doesn't exist. Do we ever take 1,000 samples? Why would we do that? Yeah, why would we do the same experiment 1,000 times? In healthcare, we wouldn't. But if someone was interested in maybe looking at quality control on a GM truck line, maybe they would want to do the experiment over and over and over again and talk about how many times are we putting an ignition switch in here, for instance, that doesn't work. So repeated sampling, which is what hypothesis testing is based on, this repeated sampling. Thousands and thousands of times I'm going to perform the same experiment. It doesn't make sense for what we do because we actually only take one sample. We do the experiment once. Maybe we replicate, but we're going to replicate, the experiment maybe a second time, not 1,000 times. But repeated sampling does make sense when you're looking at things like quality control. Regardless, your question is a great one, and I'm going to show you in a moment when you would what we call recalibrate. And that's when this is what we call the null hypothesis, and the null hypothesis is not true. And what we end up with is data that's like far to the left or far to the right of the population, and it doesn't look like it came from that population. So I have an example of that in a moment. Yes? Say that one more time. This population doesn't have a size. What I did was generate a random number using a normal distribution, and I only generated samples of size 10. This population we could think of, it's very large. It's infinity. Correct. Correct. Right. I think correct. So whenever you're doing surveys like for a poll for politics, what's really more important than the method you're using to estimate is how you collected the respondents, because there's huge potential for bias. There's a whole set of statistical methodology for surveys to adjust. For instance, if you know your sample is 70%, if you know your population is 70% Caucasian, 20% African American, 1% Hispanic, for instance. But then whenever your company goes out and actually takes a survey, if you look at the breakdown of race in your sample, and it's very different from the breakdown of race in the population, you're going to have to make some adjustments, right? Because we do know that race can affect, doesn't really affect, but it's associated with people's political leanings, right? Sort of a surrogate marker for it. Does that make sense? So there's a whole set of methodology about how to correctly take a sample from a population when the population is huge, and then when you do the analysis, how do you make your analysis, how do you adjust what you found in your sample to make it reflect more accurately what you would have found if you'd seen the whole population. That probably didn't answer your question, but we're going to get in a moment to talk about what are called confidence intervals. And the confidence interval there, so whenever you hear in political polling, they'll say, you know, like in the last election, it was Barack Obama was ahead with 50% or 49% of the vote, and the margin of error, they always have in parentheses, plus or minus 2 points. That plus or minus 2 points takes into account what I just said. If they only polled 75,000 people from the general population, the margin of error would take that number into account. It sort of scales the estimate. What they're saying is it could be 50, but it could be as high as 2 points more than that or 2 points lower than that. That's why whenever we have elections that are very close, it's a toss-up. Even when the polls are separate and it looks like someone's ahead, because they only sampled 70,000 people, the interval estimates overlap, and so what ends up happening is you actually have the reverse relationship. So that's a yes.
It would be helpful for the recording if you would repeat the question.
I'm trying to make my answer as standalone as possible. So hopefully it is. But I will try to repeat the questions from here on out. Okay, so the mean of this histogram, and again, this is based on a simulation that I did, is essentially 0. The standard deviation of these sample means, and again, remember what a standard deviation represents. It represents this distance, the distance between the mean and mathematically an inflection point on this curve. But the standard deviation here is about this distance, and it's about 0.49. So of my sample means, from samples of size 10, there were 1,000 of them, the average value was 0.0025, negative 0.0025, and they varied plus or minus 0.49, essentially 0.5, in terms of the same units as this score. Sample means, I never got a sample mean smaller than, I don't remember what exact minimum and maximum was, but if you look, 100% of my 1,000 sample means are within plus or minus 1 standard deviation of the true mean. And again, this thing is called a sampling distribution. So I don't know if anyone's ever said that term to you or if you remember it from your stats class, but that's what the sampling distribution is. And why am I spending so much time on it? The sampling distribution is what everything about hypothesis testing, it's what matters, because it's what's generating everything that we use to talk about statistical significance. It tells us if we're taking samples of a certain size from a population with certain characteristics like a mean of 0, what are the most likely values of the sample mean that could be drawn from this population? Values in this range. How variable is the sample mean from sample to sample if we're taking samples of size 10? Well, that's what that standard deviation of sample means is telling us. And then here's where the light bulb, I hope, comes on. This is what we're always asking when we do hypothesis testing. What are the chances that the sample mean I actually got from my sample came from that population? So if my sample mean is out here, everyone knows how to read a histogram. How many sample means out of 1,000 had a value that far away from 0? Not very many, right? In fact, if I wanted to count the number that are here or out here in the tail, that would be what I call an empirical p-value. What if I got a value from my sample that was right here, very close to 0? How likely is it that I would get a sample from that population of size 10 that would give me a sample mean here? Pretty likely, right? In fact, the histogram is very tall over that spot. What about way out here? Again, not very likely. There were not very many samples from the 1,000 that I actually took that had a sample mean that negative. So again, I want to reiterate, the sampling distribution is a mathematical or theoretical thing. It really only exists when you're doing things like quality control and you are truly repeatedly sampling a process and recording something. But we only do that once. So we like to rely on mathematics to tell us what is the behavior of the sample mean. And the mathematical theorem behind this is what's called the central limit theorem. Does anyone ever recall hearing the term central limit theorem? All it tells us is that the sample mean, x bar, when drawn from a population, in samples of a certain size, let's say 10 or more, its sampling distribution will look like this thing. The sampling distribution will be centered at the true mean, and it will have a standard deviation that's a function of the standard deviation in our population. And I'll show you that now. This is how, again, the sampling distribution is a theoretical thing. It's a mathematical formula. And this is that formula. Okay? If this is my population, and it has a mean of 0, if I take a sample of size 5, the sampling distribution for the sample mean will also be centered at 0. If I took a sample of size 10, it would be centered at 0. The mathematics tell me that. If my population has a standard deviation of 1.5, then the standard deviation of the sampling distribution for samples of size 5, now stop here, because there was 1,000 samples of size 10. The n is not the number of samples that you take, it's the number of subjects in your sample. We only ever sample once, right? That's why there's not a histogram here. If I take a sample of size 5, the mathematics tell me that this is the behavior of x bar from samples of that size. It's centered at 0, and it has a standard deviation of the original standard deviation divided by the square root of the sample size, which is 5. So notice the sampling distribution is more precise than the original population, but it's centered over the same mean. What about whenever I take a sample of size 10? What does the mathematics tell me? The center of the distribution is still at 0, but now the standard deviation of this distribution, the distance between here and here, is 1.5 over the square root of 10. It's actually smaller, more precise. More precision when I have greater sample sizes, right? Does anyone recognize, I know there's some Greek letters here, this formula? It has a name, and you guys report it very often in your standard error. Yay! Standard error. So in English, what is the standard error? It's the standard deviation of the sampling distribution, right? It's this distance. So it tells me if I were to draw samples of size 5 from a population that looks like this, I'm most likely to get a sample mean between plus and minus 1 standard error, or plus or minus whatever this is. I should have calculated it out for you. 1.5 over the square root of 5. If I go out 2 standard errors, or 2 standard deviations, then I'm going to encompass 95% of all possible sample means that I could get from that population if I'm taking samples of size 5. So the standard error of the mean is the way we talk about sampling variability. Everyone remember slides back, sampling variability? Your sample was size 10, mine was size 10, and our means were different. If you had a sample of a size 1,000 and I had a sample of size 1,000, our means would be more similar because there may be some overlap, right? So there's less sampling variability. That's why you see literally less variability in these distributions. And that's why fundamentally we like bigger sample sizes. Why? Because our estimate that we draw from the sample is going to be closer to the truth in larger samples than it would be in smaller samples. So when you're reporting the standard error of the mean, you're essentially telling the reader of your work how reliable your estimate is of the true mean. If you have a really large standard error, they're going to go, wow, it's not a very reliable estimate. Their sample size maybe was too small, or there was too much variability in their measurement, that kind of thing. So again, the take-home message of this introductory part is the sampling distribution of a statistic. Now, I've shown it for the sample mean, but any statistic, the sample response rate, the test statistic, like a T, all of them have mathematical functions that relate what their behavior looks like to the size of the sample that you actually collected and the population from which you drew the sample. So the sampling distribution of any statistic is fundamental to everything we talk about in statistics. Well, for the remainder of this course, because the remainder of this course is hypothesis testing, which is based on a sampling distribution. So for instance, when we talk about power, when we talk about type 1 error, when we talk about sample size, when we do test statistics like the T or the F in ANOVA or a chi-square, those are all coming from a sampling distribution. When we talk about p-values, those come from the sampling distribution. Standard errors, we've already shown. Confidence intervals. If you're familiar with the relationship between a confidence interval on a sample mean and the standard error, you'll recognize that in the formula for the confidence interval for a sample mean, the standard error is in there. It's just multiplied by some confidence, some number that reflects your confidence in it. So we'll circle back around to this concept for our first few examples in hypothesis testing to kind of reinforce the mechanics, and then I'm going to leave this behind because I hope after a couple of examples you'll have at least an understanding of what's going on. I'm going to stop there and see if there are any questions. No? Okay. So let's move on to actually doing hypothesis testing. So again, we're usually interested in something called a population characteristic, which we'll call from here on out a parameter. Parameters, when we're doing hypothesis testing, we assume that they're a number. They're a fixed number, like the average BMI in the U.S. is 20, I don't know, what would be a good BMI? 20-something. It's a number, and it's fixed, and it doesn't vary. It stays right there. So it's just like my BMI is a number. So our research questions will involve these parameters. What's the average BMI among fifth graders? What's the proportion of hospital patients that acquire a hospital-based infection? To determine these values exactly, we'd have to look at the entire population, right? We'd have to do a census. But very often, we don't have the money, the time, the ability to look at the entire population, so we take a sample of a certain size that's feasible and try to make inferences about the population. So our sample statistics, again I want to reiterate, are really just random variables. The sample mean, the sample proportion, the test statistic T, those are all functions of our sample data. So if our X here is that the CS score from the previous example, to compute the sample mean, I just add them all up and divide by the number of subjects in my sample. That's a function of sample data. If a quantity is a function of sample data, it will vary from sample to sample because of sampling variability. Real quickly, let's make sure that we remember null and alternative hypotheses. The alternative hypothesis is usually, in most cases, what we actually are trying to prove or support. For instance, I think my treatment is better. My treatment is just as good, but it costs less. X is associated with Y. So it's very often a statement of some difference or association between variables. The null hypothesis is the opposite. So if you're trying to prove that there's an association, the null hypothesis will state that there is no association. If you're trying to prove there's a difference, the null hypothesis will be a statement of no differences, equality. The null hypothesis is what we actually have to test. So in our cookbook, this is step 1 in our recipe. Briefly again, we can have one-tailed and two-tailed hypothesis tests. How do I know if I have a one-tailed test and what does it look like? A one-tailed test means that you have a hypothesis that says, I'm going to see an effect in a specific direction, like an increase or a decrease. So if I said that giving this drug will result in a decrease in blood pressure, then I'm going to have that less than sign. The mean blood pressure will be less than some other blood pressure, either a number or a control group. If I said it was an increase, it would be the greater than sign. Or I could have a two-tailed hypothesis, where the direction of the effect is unknown, or maybe you have an idea but you want to be conservative and catch the evidence in either direction, then you would have that not equal. So if I said that this therapy will result in a different response rate than the current standard of care, I'm not saying whether it will increase or decrease, just saying it will be different. So my alternative hypothesis will include a not equal sign. The hypotheses that we have to actually explicitly write out are statements concerning those characteristics of the population, like the population mean, the population variability, some population response rate or proportion, population correlation or association. So in statistics, we tend to represent these pretty standard by these Greek letters, mu, sigma, pi, rho, or maybe beta in a regression model. So I'm going to try to stick to the standard notation, but please don't get bogged down in the letters and just try to focus on the concept. So for example, It's hypothesized that the response rate for the experimental therapy is greater than that of the current standard of care. So my response rate is a proportion. And what I'm saying is that the proportion of subjects who respond should be greater in one group than in the other. So that's what this looks like. It looks like a mathematical equation. But this is what the statistician actually needs to be able to get from their conversation with you in order to formulate the hypotheses and figure out what you're actually testing. So what's the appropriate method? What's the appropriate sample size? Things of that, for instance. So the fact that we're showing here that there is a difference or an association between treatment and response rate, that's our interesting, that's the thing we try to support, so it's the alternative hypothesis. The decisions that we make could result in correct decisions or in errors. So type 1, type 2 errors are important that we control them at low levels. Again, remember that type 1 error is incorrectly rejecting a true null hypothesis or concluding that there is a difference when no difference really exists, or an association when no association exists. A type 2 error is failing to detect a difference, if there really is a difference there. And that's directly related to the power. You want a powerful experiment because you want to be able to find the difference as significant if the difference actually exists. So again, I've only modified this slightly from the last lecture to put in the word population and sample. So the truth is whatever the population is. The conclusion is whatever the sample supports. Now, what we're going to do is we're actually going to say what the truth is when we do hypothesis testing, because we really don't know the truth. We don't know whether there really is an association or not. But we're going to assume that the truth is the null hypothesis. And what that will do is create at the top of that picture what the population looks like. It will center that nice normal distribution over our hypothesized value that's stated in the null. And then we're going to grab a sample randomly from that population. And we're going to see if the data that we got looks like it came from that population where the sample, or excuse me, where the population average is whatever we said it was under the null hypothesis. So here's our recipe. We're going to formulate first and state our null and our alternative hypotheses. Number 2 is fundamental because it starts off and it creates that distribution at the top of the previous slides. It sets up the population. We're going to assume the null hypothesis is true. In step 3, we're going to collect the evidence, which is collecting a random sample from the population, computing the appropriate statistic from that sample, like the sample mean, computing the appropriate test statistic if we're doing a test. A test statistic just helps us quantify how strong our evidence is for or against a particular theory. We're going to compute the p-value, a confidence interval from the sample, and then we're going to make a decision in step 4. We're going to determine if our level of evidence is strong enough against our null hypothesis. If it is, then we're going to reject the null hypothesis and conclude in favor of the alternative. But if it's not, then we're going to fail to reject the null hypothesis. The criteria for that is comparing our p-value to our pre-specified value of the type 1 error rate. And we'll talk about that in a moment. So let's go back to our TBI example. So this is just a reiteration of the previous slide. We have traumatic brain injury sufferers who have chronic cognitive impairment. We're going to measure cognitive status using this score. We'll call it the CS score, that has a mean of 0 for normals. For normal healthy people, it should be 0. And for people who are cognitively impaired, it should be negative. So here's our small study to look at this. We have survivors of moderate or severe TBI. We have 44 of them. And we also have healthy controls, 36 of them. Recruited, we record each of their CS scores to measure their cognitive impairment. So let's talk about specifically what the statistician is pulling from your information. The statistician is looking at your sample sizes. The statistician is saying, okay, what is the outcome? The outcome that you're actually interested in is this CS score. Is it continuous? Is it binary? What is it, where does it fall on the level of measurement scale? Can we assume that it's normally distributed in this population? What is its meaning? For instance, values of 0 should be measuring normal cognitive status. Values less than 0 would indicate impaired cognitive status. And we're really only interested in the negative, right? What is the characteristic of interest? What's the population parameter? Because that tells us what sample statistic we're actually going to use. Well, we're interested in the mean score, cognitive score, in the population. Specifically, the population average score of survivors of moderate or severe TBI. We're going to focus on that characteristic at this time. So I'm going to state a null and an alternative hypothesis. What do we suspect? Let's suppose, again, not a lot's been done, but we suspect that using this score that we should see in this population of TBI survivors an average cognitive status score less than 0, right? Because that would indicate that they have impaired cognitive status. That's actually what we suspect, that mu is less than 0. But what do we have to assume for hypothesis testing? The opposite, right? So the opposite is equal to or greater than. So what this is saying in English is that if I take the population of TBI sufferers, I'm going to get an average cognitive status score less than 0, which would show that they have cognitive impairment. The null hypothesis that we're going to try to disprove says if I take that population of TBI sufferers and compute its average score, I'm going to get a value that's either 0 or greater than 0, which would indicate what? No cognitive impairment. That's not what we think is actually going to happen, but we have to assume this in order to test it. So, again, what's the purpose of the null hypothesis and why is it fundamental? Because it sets up that population. Does everyone see this and recognize that it looks just like the beginning of the lecture? The x-axis is the cognitive status score. The null hypothesis places this distribution where it needs to be. We're going to assume that in TBI sufferers that the mean cognitive status score is 0. The standard deviation is 1.5. 95% of them should have a score between -3 and +3. So again, there's that population set up thanks to the null hypothesis, centered over 0. Now again, this is not that paper's real data. I generated data based on their summary statistics. So the null hypothesis says the mean is 0. I collected a sample of moderate to severely impaired subjects, 44 of them. There's 44 different scores here, and I'm dropping them down into a histogram. I want to look at this. And visually, in this histogram, this is 0, this is normal, this is the sample mean for my 44 subjects. Does it look like my sample data came from a population where the mean is 0? To me, it looks like it's what I would call miscalibrated using your terminology, right? It looks like the mean is actually less than 0 in this case. Everyone see that? But how do I know if my evidence in this sample is strong enough for me to say that this is actually not what the population looks like? Well, that's where this bottom thing comes in. Remember that sampling distribution? I'm dropping my sample mean, the only one that we ever actually collect, on top of an empirical sampling distribution. But the theoretical sampling distribution would actually just be a smooth line like that. But let's look at it like this. For my particular sample mean, which is represented by yellow, does it look like it came from this distribution of sample means? No. This distribution of sample means, which we call the sampling distribution, is what the distribution of means would look like if I were truly taking samples of size 44 from a population with a mean of 0. So I should have gotten values between here and here for the sample mean. Those are the most likely values that would have been generated. But I got a value way out here. And again, this is the mathematics. So the question that we ask ourselves when we do hypothesis testing, when we're trying to actually come to a conclusion, what are the chances that my hypothesized population actually generated that sample data that we collected? And when we say chances or likelihood, we're talking about probability. So we have to get something like a p-value to quantify those chances. We also have to use things like test statistics. Test statistics are very useful because they help us think about the strength of our evidence. So in the case of a continuous outcome like CS score, where I'm interested in the population mean and I have approximately normal data, the appropriate test statistic would be the t. Look at the bottom of the t. What does that thing look like? Standard error, right? It looks like a standard error. Now again, don't get bogged down in the notation. There's an S here instead of a sigma. And the reason that is because we never really know what the population standard deviation is. So we estimate it using the sample standard deviation. But regardless, the bottom of this formula is the standard error of the sampling distribution. Okay? So what is the t doing when we use it in this scenario? The top of the t is a difference between the sample mean and the mean of that population at the top of the picture. So essentially, when I take my sample mean and I subtract out what I've hypothesized the mean of the population to be, when I take that difference, that gives me like a distance between the hypothesis and my evidence. If that distance is small, what does that mean? That means the evidence and the hypothesis kind of support one another. If that distance is large, then I have some disagreeing sources of information, right? However, we're all aware of the fact that differences between two values are only meaningful in the context of the natural variation in something, right? So if I have a measurement like, let's say I'm looking at the time it takes to complete a task. It took me 10 minutes, and it took you 7. So there's a 3-minute difference in that. We don't know if that difference is large or small unless we understand the behavior of that outcome. So if the variability in that outcome is very small, let's say plus or minus 15 seconds, then that's a huge difference in 3 minutes. But if it's plus or minus 6 minutes, then that difference really isn't all that meaningful. So the reason the t is not just this top part, but it also takes into account this bottom part, which is the standard error, is because we want to scale or standardize that difference by one standard deviation of that sampling distribution. In other words, we're kind of scaling it by the sampling variability or the reliability of our sample mean, pulling out that one source of variation, standardizing it so we can really think about what that difference between x bar and mu really means. So let me give you an example. How do we interpret it? This is that test statistic. The sample that I collected of 44 subjects gave me a sample mean score of -0.7. So there's my x bar. I'm subtracting out what I hypothesized the population to look like, which was 0. The standard deviation of my scores in my sample of 44 was 0.72, and I'm dividing by the sample size, which was 44, square root. So my t, when I do the math, is -7. So before I standardized that difference, I had a difference of -0.7. After I standardize it, I have a difference of -7. I would argue that this thing right here is essentially meaningless until you divide it or standardize it, give us some way to interpret it unitlessly. So the -7 actually means, in English, that the sample mean score for my sample of size 44 is 7 standard deviations below the hypothesized population mean score of 0. Why is it 7 standard deviations? Because this is the units I want to measure it in. That's why I'm dividing by standard deviations of the sampling distribution, or standard errors. So that the test statistic, and this will be true in general for the rest of the course, the test statistics that we compute, their value represents the number of standard deviations. And we all understand standard deviations. The number of standard deviations between our evidence, which is the sample data, and the hypothesized value from our null hypothesis. The bigger the test statistic, the further away the two are, and the more evidence you have against the null. So if I were to say that I got a value that's 7 standard deviations below what I expected, what would you say? I would say you expected wrong, right? My hypothesis is probably not accurate. That's why the test statistic is very useful. But how do we get the p-value? The p-value tells us how likely it is that a population with a mean score of 0 generated a sample that was size 44 with a sample mean of -0.7. The answer to that is not very likely. And I know that just because my test statistic is -7. But to get a p-value, I need to think about what's going on. Here's my population, centered at 0, standard deviation of 1.5. I let the mathematics kick in because I'm not doing 1,000 different samples and figuring out where my particular sample falls on that histogram. So I call on the central limit theorem to tell me what's the distribution of sample means if I'm taking samples of size 44. Once I call on the mathematics, then I go and I grab my actual value that I observed for my one sample, which was -0.7. This is transformed on the t-scale now. It's 7 standard deviations away from the mean. And then the p-value helps me quantify, additionally, how strong my evidence is against the mean being 0. And the p-value, now that we know what a sampling distribution is the area in the tail of this distribution in the direction of our alternative hypothesis. So if you remember, our alternative hypothesis was that these TBI survivors have impaired cognitive status. They should have a value less than 0. And I think that there's pretty strong evidence for that here. Do you all see that? Specifically, the p-value is so small I had to cut it off at 4 digits. It's less than 0.0001. And what that's representing is the area, which you can't even see it because of this distribution, by the way, does not stop here. It goes out to negative infinity and positive infinity. But the values, the probability in that tail is so small that you essentially can't even see the tails now. But that's where our sample mean fell, negative 0.7. The area in the tail from here to negative infinity is less than 0.0001. So what would you conclude? Would you reject the null hypothesis that the mean is 0 or greater? Yes. Yes, you would. How do we make that decision? Before we started the study, hopefully we designed it with a particular effect in mind, and we specified that we were going to test this hypothesis at a specific error rate, alpha. So very often alpha is 0.05. We've talked about why alpha shouldn't be 0.05 in certain circumstances, but let's assume that it's 0.05 because that's the general rule. If your p-value is 0.05 or less, all that means is that the chances of getting the evidence that you collected from your sample, given the null hypothesis is actually true, are really very small. They're less than 5%. In English, your observed data conflicts with that null theory. Your observed data actually supports what we called our alternative theory, which was the thing we actually wanted to show. Since our data, which is our evidence, was actually observed, and our theory, the null hypothesis, is just a theory, we choose to believe the empirical evidence, the data, and then we reject the null hypothesis in favor of the alternative. That's not always the case, though, right? Very often we don't get very strong evidence. What if our evidence had not been in as great of a degree of conflict with our theory? What if we got from our sample of size 44 a mean score of negative 0.1? Notice the sampling distribution looks exactly the same as it did before because my sample was still size 44. The mathematics is the same. But now that yellow line representing where my evidence is actually kind of within the normal range of that distribution. So in this case, our evidence does not conflict with this null theory. In fact, if I were to compute the test statistic for this, it would be small. It would be less than 1. How do I know t would be less than 1? In absolute value, I should say. It would be like negative point something. How do I know that? What is t? What are its units? Standard deviations, right? This gray line represents plus and minus 1 standard deviation. And this is between 0 and minus 1 standard deviation. So I know my t would be less than, it would be closer to 0 than negative 1. So if I were to tell you that I have a subject here whose value is 0.7 standard deviations away from what we expect, you would say, okay, that's pretty normal. That's okay. Same thing whenever you get evidence in a hypothesis test. So it turns out if you compute the p-value for this, the p-value is the area under this curve in the tail in the same direction as our alternative hypothesis. So it's this amount of area. Now the total area under this curve is only 1 because it's a probability distribution. Probability can only go up to 1. So this proportion of that is definitely, even visually, much greater than 0.05, right? It's actually getting pretty close to half, 0.5. So then we would, in that case, fail to reject. If your p is large, that tells you that the chances of you getting the evidence that you collected from your sample, given the population looks like what you specified under the null, that those are not small enough for us to conclude that the hypothesis is improbable, which is really what we wanted to do in the first place. So we fail to reject the null hypothesis. I have a picture here, just a generic picture to show you kind of how we know where our evidence needs to be before we reject or fail to reject. For this specific scenario, remember the alternative hypothesis was for negative values. When we specify alpha, we basically specify that cutoff point at which we have met the threshold of evidence necessary to reject the null hypothesis. So if I get values of our sample mean here or more extreme, then I'm comfortable at that point saying that I can reject the null hypothesis. However, if it's here, it's still less than 0. It's still in the direction that I thought, but it's not strong enough for me to say with certainty that I would reject that theory. It's still plausible that I could have gotten a sample from that distribution that provided the evidence that I actually observed. So this is what we call the rejection region, and it's defined specifically by the alternative hypothesis, so which direction, and by the size of your type 1 error. How do we know, once we've made a decision, if it was correct or not? And the answer is we don't, until you replicate and replicate and replicate and replicate, and you get pretty standard evidence with nothing conflicting. Even then, you don't know with 100% certainty. There may be something else going on that you don't know about. But the answer is we never really know the truth until we can observe the entire population. If alpha, if we specified that we wanted it to be 0.05 or 5% chance type 1 error, all that means is the chances of our decision being an incorrect rejection of a true null hypothesis are no greater than 5%. In other words, the chances of concluding that that score is less than 0, when in fact the score is not less than 0, are no greater than 5%. When would we make an error in this case? What would that error look like? An error could be made if we collected a sample of size 44, computed the sample mean, and it was negative 0.7, and we concluded from that evidence that we reject the null like we just did because we had a mean of negative 0.7. But in fact, the null hypothesis, that distribution at the top is centered at 0, was actually true. There's always a chance that you could get a sample that gives you evidence that conflicts with that when in fact the real population looks like that. So setting up your experiment in the appropriate way protects you by making the chance of that occurring very small. It's always best also when you have sampling variability issues to gather samples that are an adequate size. There are other issues, however, that could cause this error to occur. Primarily, something like bias. So let's think about this. What if, and this happens a lot, what if the score that we're using, this cognitive status score, really isn't measuring what we think it's measuring? It's not really measuring cognitive status the way we think it is. In other words, what if a score of 0 really doesn't reflect normal cognitive status? If you think about our experiment, what did we do? We had a single group, right, a single population. We assumed that our outcome meant something, that at 0 it would identify normal cognitive status. And then we computed cognitive status for our impaired subjects and compared that to this assumed value of 0. How could we modify our experiment to tackle this problem? We still want to use the CS score because it's easy. Everybody's using it. But it's not calibrated correctly. How could we adjust what we just did? Yes. Who said that? A+. Control group. What kind of control group? Healthy normals, right? If we actually had another random sample of healthy normals and we used this CS score on those healthy normals, and then we compared the average CS score in TBI survivors with the average CS score of our healthy controls, then we've eliminated that problem, right? It doesn't matter what CS score, where normal is, because we're going to actually get a measure of normal using a sample. Now, there are other issues, sampling variability and things like that, that are not addressed in this, but that's the reason why we have a control group, because there could be potentially bias in this measurement. For instance, if negative 0.5 actually indicated normal, then it would appear in that one sample test that we had an effect, when in fact it was just the bias in the measurement scale. That's why a control group is very, very useful. In addition to reporting p-values, you should always report an effect size. The reason you want to report what we call an effect size is because people want to know, was this clinically significant in addition to statistically significant? You'd be surprised how many results are published with just p-values and no way of knowing whether or not the study may have been just overpowered, or whether the difference really was meaningful or the association really was meaningful. But what is a confidence interval? I think I've already demonstrated to you all that the p-value and the standard error are not as straightforward as we once thought. Neither is the confidence interval. The confidence interval is also based on the sampling distribution. So that mathematical mechanics behind the p-value and the test statistic and determining whether or not we can reject or fail to reject, that same machinery is giving us the confidence interval. So I wanted to show you what I mean by that. This is the sampling distribution of means. Suppose we all took a sample. Everyone in this room took a sample of size, let's say of size 10, from the same population. We did it independently, and we all computed a confidence interval for the mean. If the true population was centered at, let's say, 0, then 95 of us should have confidence intervals that cover or include that true value of 0. 5 of us out of the 100 will not. So for instance, number 4, whoever number 4 is, your confidence interval just by chance did not cover the mean. You did the experiment the exact same way I did, but because of sampling variability, you missed the target. This person just barely missed the target. This person just barely missed the target. The rest of us, we did a pretty good job. Our mean, our sample mean, which is you generally, in this case, it's the center of this line, varies, as do our upper and lower confidence limits, but we cover the truth 95% of the time. So all a confidence interval is, when we talk about confidence, we're talking about the procedure and how it would perform if we did it over and over and over again. It's the same way we talked about the sample mean, taking a sample, computing the mean for an infinite number of samples from the same population. So being 95% confident means in 95 out of the 100 samples, our interval contains the true unknown value of the parameter. However, in 5 of the 100, it doesn't. Or 95% of the samples that could be drawn from the population will contain will create an interval that would contain the true value of the parameter that we're trying to estimate. 5% of them won't. So our confidence is in the procedure that we're using because it performs well most of the time. But we're not really talking about our specific confidence interval. Just like when we had in the few slides back, how do we know if the decision we made was the correct one? We don't. How do we know if our interval estimate, our particular interval estimate, contains the truth? We don't. We just know that the chances of it not covering the truth, if we've done the data collection appropriately, are very small. But we can't say things like the probability that the true mean is between some number and some other number is 0.95. That's not an accurate statement. We can just say that this method performs well 95% of the time for 95% of samples that could be drawn from the population. Did that confuse you enough? So we have to be careful about how we word our conclusions to make sure we don't talk about things like the probability. Probability is a statistical term, and it has meaning, and this is actually not the meaning of a confidence interval. That's why we say confident, because it's ambiguous and vague. So again, please always report a confidence interval along with a p-value or some other measure of effect size whenever you're reporting a result so people can interpret the clinical significance of your results in addition to your statistical significance. If you wanted to know what these intervals are actually computed, what do they look like? And I should have put this in. I don't know why I didn't. X bar, your sample mean, plus or minus. I'm just going to put a number in here for now and talk about what that number means. Sorry, it's hard to write with a mouse. Everyone see what this last term is? It's the standard error of a sampling distribution. So this takes into account the size of your sample, the variability in your sample, and how reliable means drawn from populations of this size should be. So if your sampling distribution is not very precise, neither will your confidence interval be. They're directly related. So we know that this takes into account sort of the behavior of X bar, of the sample mean, sampling variability. What does this thing do? Anyone remember? Why do we multiply by another number? That's the confidence part, right? So if you remember, there's kind of rules of thumb. If you wanted 95% confidence, you put in a particular number. If you wanted 99% confidence, you put a different number in. It adjusts the width of the interval for your level of confidence. So there's two things that go into a confidence interval: the confidence and the reliability of your estimate. So really wide intervals usually are not very useful. And that's usually because your sample size was too small. So your sampling variability, or your standard error, is big. Narrower intervals are usually very useful because you probably had a larger sample size, so you have better reliability in your estimate, and it's reflected through the precision of your interval estimate. Any questions about that? Okay, let's do a couple more examples. Which test do I use? Remember when we talked the first couple of lectures, you have to first identify what does your data look like? What kind of outcome are you looking at? We already knew in the cognitive status example that was a continuous outcome. Cognitive status of 0 really didn't have, I mean, it had a meaning, but it didn't mean a lack of cognitive status. So it's not ratio, it's interval. So identifying where it falls on the scale automatically eliminates probably 99% of the methods out there and focuses me in on a few. Then I determine how many samples do I have. Am I doing a one sample test like I did in the cognitive status example, where I just had one sample of impaired subjects? Or am I doing two samples, where maybe I have a control group? Are my two samples two separate groups of subjects? Are they the same subjects? They're just going to get both treatments. We have to determine whether or not we have related samples or independent samples, because that would affect the type of analysis that we would do. The different types of tests based on the type of outcome you have are listed here. So categorical outcomes are the nominal and ordinal. When we have categories like a yes, no, or male, female, or complete response, partial response, stable disease, failure, those things we tend to describe using percentages or proportions. So it makes sense then if we're asking questions about, is there a difference in this population from some other known population, that we would talk about hypotheses in terms of proportions. When we talk about proportions, the sample statistic is just a proportion. And we use, for instance, a binomial test or a z-test if we have a large enough sample. And again, this is for one sample methods. If we have ordinal data, and we have this a lot, Likert scale data. So if you're asking a respondent how much they agree or disagree with a statement, and that can range from 1 to 5, from very much disagree to very much agree, that's ordinal data. Those responses are categorical, but there's some ordering in them. Then you would want to do something like a median test or a Wilcoxon signed rank test. This is actually a non-parametric test, so it doesn't matter what size your sample is. If you have continuous outcomes like interval or ratio, we're very often interested in the mean. More mathematical things can be done when you get to continuous outcomes than what you had available to you with categorical outcomes. So the most common method for one sample continuous data is a student's t-test, which tests whether or not your sample mean is equal to some number. In the example that we had before, this number was 0. The statistic obviously is the sample mean. Now, we talked last time about parametric versus non-parametric tests. Instead of a student's t, for instance, if your data is not normally distributed, or if you have a very small sample size, you would want to use a non-parametric test like a Wilcoxon test. And the same methods really will be used for ratio data, where that 0 has meaning. What if we have two samples? Kind of like in our cognitive status example, we could have had an impaired group and a control group. And we're going to compare a rate, a nominal yes-no outcome between the two groups. Then we would be hypothesizing that the rate of response in one group is equivalent to the rate of response in the other group. And that would be through a chi-square test usually. But the chi-square test requires that you have a large enough sample that you don't violate its assumptions. You could also use what's called a Fisher's exact test, which doesn't have any of those restrictions on sample size. If you have ordinal data, Likert scale data, for instance, and you're comparing the Likert scale responses of one set of subjects to those of another set of subjects, you could use something like the median test, which is also a non-parametric test. If you have continuous data, we've already been in this realm this morning using student's t, but now instead of hypothesizing that the mean of a population is equal to some value, you're hypothesizing that the mean of a population is equivalent to the mean of another population. And you're going to actually have samples from both of those populations, and you're going to compare them. Sort of like what we talked about when we would use a control group for the issues of bias that we talked about in the previous example. So when you're doing this, the most common parametric method is the student's t-test for 2 independent samples. If you have issues with sample sizes, when you have small samples, or if you can't meet the assumptions of the t, which requires approximately normal data and equal variances in the 2 groups, then you would want to use a non-parametric method like the Mann-Whitney test. And notice that it's the same for the interval and ratio data. When you're comparing central tendency, in other words, comparing an average for populations between groups, this is the flow chart. First, determine the number of groups you have. Here I'm comparing 2 versus greater than 2. Simply because of space, this flow chart could get huge. Let's focus on the number of groups that you're trying to compare. Let's say I have 2 groups, a treatment and a control. I want to then look at the assumptions of all these parametric tests, which is generally, is the data, if it's continuous, normally distributed approximately? And do we have, equal variances, or are samples independent or dependent? So if I have a large enough sample and I see that I have normality, then I have to then determine my 2 groups. Are they independent samples or are they dependent? Let me give you an example of independent samples. 2 independent samples, 1 of impaired subjects, 1 of healthy controls. And there's no matching, no relationship, no nothing between the 2. Dependent samples could be, I have a single sample of impaired subjects. I measure them pre-intervention, then I intervene and try to affect something, and then I measure them again post-intervention. So technically I have 2 different groups here, right? I have pre and I have post. However, the 2 groups consist of the same subjects. That's what's called dependent samples. So if you do repeated measures, if you're repeatedly measuring the same subject, you're going to have dependent samples. So you have to be careful and make sure that you identify that. You wouldn't want to do a 2-sample t-test on pre-post data. You would do what's called a paired t-test on pre-post data. The paired t-test takes into account the fact that a subject's impairment prior to the intervention has some impact on their impairment after the intervention. So if they have low impairment before versus someone who has high impairment before, that can explain part of their response to the intervention. So there's a correlation or an association here that you have to be careful that you take into account for, which the 2-sample t does not, but the paired t does. What would be the impact of doing a method that ignores that correlation when you should have been doing a method that accounts for it? Does anyone know? You actually lose power because you're basically treating this, you're ignoring the correlation. If you took into account these correlated observations and understanding that person 1 here is the same as person 1 here, you have a more powerful test of differences than you would in a 2-sample t. So you would lose power, essentially. So again, number of groups, 2. If you meet the assumptions, or you have a large sample size, then 2-sample t or paired t for independent and dependent samples. If you have a small sample size, if it's too small for you to really test whether or not you have normality or equal variances, or you have data that just will not behave normally, no matter how much you try to transform it, then what you want to do is use a non-parametric test. So again, just like before, do you have independent samples or dependent samples? If you have 2 independent samples comparing treatment A versus treatment B, you use a Wilcoxon sign rank test. If you have dependent samples, like a pre-post, you use a Wilcoxon rank sum test. Wilcoxon did a lot of non-parametric stuff. His name is on almost every test, which is why it can be a challenge to figure out what it is you actually got from, for instance, SPSS. Was it the sign rank test? Was it the rank sum test? Which one of these is which? So, again, just another obvious issue that can arise when you're trying to identify which test to use. If you have more than two groups, and I alluded to this at the beginning, you're not going to be using T. Notice there's no T test down here. If I have group A, group B, and group C, and they're independent samples, and they meet the assumptions of a parametric test, then I can use what's called analysis of variance. ANOVA and the two-sample T have a one-to-one relationship. They're basically doing the same thing. So everything that we talk about for a T-test is the same kind of mechanics underlying an ANOVA, only it's transformed a little bit to account for the fact that you have more than two groups. If you have large samples, you meet the parametric assumptions, but your samples are, for instance, dependent, like you're doing repeated measures, like the pre-post that I talked about before, or you have a crossover design where subjects act as their own control, then you use what's called a two-way ANOVA. For the sake of time, we will not get into this. I'm going to demonstrate the basic one-way ANOVA, and then if you have questions, I can always meet with you all individually. There are an infinite number of ANOVA models. There is a class in just analysis of variance, if you're interested, that's taught in the spring. If you have small sample sizes or data that's not normal, then you can use non-parametric methods like the Kruskal-Wallis test, which tests the equivalence of 3 different or 4 different treatment groups when the groups are independent, or Friedman's test, which does the same when the groups are dependent. Any questions? I can provide that slide or that flowchart for anyone who wants it. Just give me an email. Let's start. We've already done a one-sample test, a one-sample t-test in our example on cognitive impairment. Let's look at a two-sample test now. Suppose we have 2 different drugs, and we're interested in looking at the clotting time of blood in minutes for subjects who are administered one of these 2 drugs. We're interested in, is there any difference? We've got 6 subjects who get drug B. We have 7 subjects who get drug G. The hypothesis is, the research interest is, that the 2 drugs will result in different blood clotting times, and that's important to know. So what we're really interested in showing is that the mean under drug 1 is different from the mean under drug 2. We're not specifying whether there's an increase or decrease in clot time because we actually want to catch either direction. It's important to us. So we're doing a 2-sided test here. To support this, we actually have to test that they're equivalent, that they're equal. So this will be the thing that sets up that population. Here's our evidence. Time in minutes, 8.8, 9.6 minutes under drug B. Drug G, 9.9, 10.4, 9.5. Since I'm hypothesizing about population means, what would happen in the general population if I put these drugs out there? I'm going to compute the sample means. So under drug B, which is group 1, I have a mean of 8.75 minutes. Under drug G, which is sample 2, I have a mean of 9.74 minutes. What we're actually hypothesizing here, and again, this is why we need to understand the sampling distribution, is that if I took these 2 populations, if I took their means, the mean clotting time under drug 1, the difference between it and that under drug 2 is essentially 0. Right? That means that they're the same. I could do a little bit of mathematics and add that over there on that side and show that it's the exact same thing as this hypothesis. So what that does is it sets up that population of clotting times centered at 0 with some unknown standard deviation. We're actually going to estimate it from our data using S. Knowing our sample sizes, 7, and 6 and 7, mathematics kicks in and I get that sampling distribution. This describes the behavior of sample means calculated from samples the same size as ours, drawn from this population. If 0 is the true population difference, then I should get sample means close to 0. For samples of size, for samples of size 6 and 7, the variability, the reliability of my sample x bar, which is the difference between the two sample means, is reflected in the standard error of the sampling distribution, which is S over the square root of n. S being the standard deviation of my data. So once I place my evidence, x bar 1 minus x bar 2, reflecting that we're trying to estimate this difference, my sample difference is actually negative 0.99. This was my evidence. But remember, I'm doing a two-sided test. I decided that before, so technically I needed to put evidence, I need to look at evidence in the tail past negative 0.99 and anything more extreme on the opposite end of the spectrum, which is anything beyond a positive 0.99. So it's the same magnitude of difference, just in a different direction. And it turns out that that's the p-value. The p-value, what is the probability of getting a difference in sample means of at least 0.99? Doesn't matter which way I subtract, because I don't care the direction of the relationship just yet. I want to catch it on either side. And that's all these statements are saying. What's the probability that if I subtracted mean 2 from mean 1, that I would get something less than negative 0.99, what I actually observed? If I subtracted, this should say, well, it could be the opposite, x2 minus x1. What's the probability that I would get something in the opposite direction of the same magnitude? If I compute that, I get a p-value which adds up this area and this area of 0.03. Just to make sure that we reflect back on what we learned about sampling distributions, the test statistic t takes the difference between our evidence and the hypothesized value, which is 0. So x bar 1 minus x bar 2 is negative 0.99. If you subtract 0, you still get negative 0.99, right? Because that's what we're hypothesizing. And then we standardize it by the standard error of the sampling distribution. Guess what this thing is? That's the standard error of the sampling distribution that the two-sample t-test uses. So it's right here. This thing is the sampling distribution of x bar 1 minus x bar 2. Just like in the one-sample test, we had a sampling distribution of just the sample mean. Now we have a sampling distribution of the difference in two means, which means it has a really crazy standard error formula. But regardless, our test statistic is negative 2.475. Does everyone remember the interpretation of that? The actual observed difference in sample means is 2.475 standard deviations below what I expected, given I hypothesized that it was centered at 0 here, that the true mean difference is 0. In order to use the t-test, which is parametric, we have to make a few assumptions. Why are assumptions critical? What is this thing down here? It's a mathematical formula, right? For those of you who've ever had a math class beyond, elementary, you know that we like to make assumptions before we go and prove something works. It turns out that the person that came up with the t-distribution first assumed that the data had to be normally distributed, and that the variances in the two groups had to be approximately equal before the sampling distribution is accurate. And it's important that the sampling distribution be accurate because it generates p-values, it generates test statistics, it generates confidence intervals, standard errors. All of those things would be incorrect if we don't check assumptions. So how do we check assumptions? You plot the data. That's the easiest thing to do, right? If I plot my observations in a histogram, if this is my sample data, and it looks approximately symmetric, I could see skewness here. I could see outlying observations. That looks normal. This does not look normal. I have skewness, meaning my curve looks like someone grabbed one tail and pulled it. I also have outliers. And this will affect the results, meaning the sampling distribution actually doesn't work in this case. You can also use something called a QQ plot. For those of you who have a little bit more advanced knowledge, it just plots your observed ranked data in terms of their quantiles or their percentiles against what they should look like if normality was met. And if what you assume and normality actually match up, then they should follow a straight line, x equal y. This can be produced very easily in SPSS. You just have to ask for it. If I saw something like this, there's that straight line. This tells me that my data, my true data, and my assumption that it's normal really don't match up. How do we assess the assumption of equal variances when we want to do a t-test? Or likewise when we want to do ANOVA? To assess that assumption, box plots. Here's group 1, here's group 2. Here's the response in group 1, the response in group 2. The way that we measure variance or spread is just how spread out are these box plots. And are they about equivalent? They're about the same size in terms of their spread, so that's fine. This would be no issues. This would be an issue, right? For class 1, the box plot is half or less than that of, the spread of it is half or less than that of class 2. So a good rule of thumb whenever you're looking at checking equal variances, actually calculate the summary statistics. Calculate the sample means and the sample standard deviations of both of your groups, and then look at the sample standard deviations and the sample variances. If you have one of your groups that has a variance that's more than 2 times the other, you violated the assumption of equal variances. So for instance, if the variance here was 4 and the variance here is 2, I violated it. Here, the variance could be 2, and here it could be 2.1 or 2.3 or 3. This is not a violation. This is a violation. I can see it visually and numerically. So if you do have enough observations to check the assumptions, then move forward and check them. If you violate the assumptions, what do? You can try a transformation on your data. For instance, you could try a log or a natural log transformation, a square root transformation. How do you do that? You just create a new column in your data set, and the column would be computed from the data. You could just say equals the log of the previous column, and that's your new data, and then you run the analysis on that transformed data. It causes issues with interpretation in terms of differences or estimates of means and things like that, but it will give you a valid p-value, and then you can go and try to retransform to talk about average responses and things like that. If you can't find a transformation that gives you approximate normality, approximately equal variances, then I would recommend you go on with a non-parametric approach. It would just be easier, and it would give you a reliable result. However, if you check the assumptions and they're feasible, then go ahead and do the t-test, because that sampling distribution would be valid and the results that you get would be accurate. For the one sample t, if we're doing a non-parametric test, we've already talked about the Wilcoxon sign rate test. For the two sample t, you can use what's called a Mann-Whitney test. All they're doing is stripping the values, the raw values from the data, and substituting ranks for those. The consequences of using non-parametric results, you get a robust result, but they are less powerful because you're stripping information from the data. How do we make inferences on more than two means? So we've seen one sample mean for one population. We've seen two sample means for two populations and looking at a difference between those. What about for three sample means? I already said we don't do t-tests when we have more than two samples because it inflates our error rates. Here's an example of smoking cessation, and then I'll stop after this for the sake of time, and we'll pick up here next time. I have three different types of therapy I'm interested in comparing. Drug, pharmaceutical therapy, a behavioral intervention, and then just literature. I'm going to randomly select subjects and then randomly assign them to one of these three groups with equal sample sizes. I'm going to record a continuous outcome, which is the percentage decrease in number of cigarettes smoked per day after 6 months of therapy. If I see a greater percent decrease, then I know that that therapy is more effective. So the question is therapy in addition to education better than education alone in getting smokers to quit? And if so, is one therapy more effective than the others? Our null hypothesis when we have more than two groups looks a little bit different than things that you've seen before. Rather than mu1 minus mu2 equals 0, we actually say that all of the means are equivalent versus at least one of the means is different. And this is called an omnibus test for ANOVA. So when we use more than two independent samples, we have to use this method. The assumptions of ANOVA are the exact same assumptions for the t-test. Approximate normality, approximately equal variances in all of your groups. All of the things that we could try to fix the data to be normal for the t-test would apply directly to this ANOVA problem. Analysis of variance, though, when you have more than two groups, it complicates things just a little bit. It's very easy to see a single difference, but it's very difficult to see multiple differences simultaneously. So ANOVA actually produces a table. The table in the left-hand side gives you what's called sources of variation. Analysis of variance is trying to take a subject's response to something and split it up into different pieces that can be attributed to different sources. So one of those sources is what we call between groups or treatment. So we think that the treatment should cause this subject's response to fluctuate in some way. In a one-way ANOVA, that's the only source of variation that we really care about. Everything else that could cause that subject's score to change or vary is lumped into something that we call within groups, or error. We just call it error statistically. So why, when we're hypothesizing about means, are we using variances? A mean square is another name for a variance. So we have this between groups or treatment variance. We have this within groups or error variance. And our test statistic F is just a relationship between those two things. A variance between groups and a variance within groups. Why would a ratio of variances tell us anything about whether or not we have a difference in mean scores? Again, What ANOVA is doing is taking a response, a score, a subject score, and breaking it down or attributing different pieces of it to the treatment and to everything else, which we call error. So, for instance, everything else could be gender. If I'm looking at cognitive status, the other things in that paper that they were looking at were education could affect cognitive status. Age could affect cognitive status. Exercise could affect cognitive status, in addition to whether or not they had TBI or not. So lots of different sources of variation in someone's cognitive status score. In a one-way ANOVA, we only have one source of interest and everything else is lumped into error. So in this case, we have the treatment variation and then everything else. It turns out using a ratio in this case works really well, because if this between group or treatment variation is a lot bigger than the within group variation, that suggests that the treatment is causing subjects' responses to fluctuate, or it's associated with. I shouldn't say cause, because it depends on the design. So what do I mean by that? Let's look at scenario 1 here at the top. The two sources of variation, the treatment variation, is represented by how different those lines are in terms of the y-axis. How much do they vary? And that's what we call treatment variation. So if I see drastic differences in the location of these box plots, I have a treatment effect, right? That's very easy to see. So the bigger difference I see in terms of where those box plots are placed, the larger my between group variance will be. What is the within group, though? What is the error? The error is within a single, let me erase, within a single group, the error variation, the variation in scores for subjects who got the same treatment, is represented by just how variable is this outcome in a group where they all got the same treatment. These are all TBI. This is what their scores look like. That is the within group variation. So think of this as a signal to noise kind of problem. If I have very large differences in the location of these box plots relative to the variability within the data, I'm going to find a difference through that ratio. That ratio will be large. However, look at scenario 2. We do see some differences in their location, right? We see increasing just like before. But what's the problem now? We've got a lot more noise. There's outliers there. A lot more noise in the data. So even if there is a treatment effect, it is very small relative to the error variation, which means there's either other things we should be accounting for, or there really is not a significant difference in these groups, or I don't have enough subjects to see a true difference. This last scenario essentially shows where there's a lot of within group variation and essentially no between group variation. Notice that the averages are about the same. So the F statistic in that ANOVA table takes into account the ratio of those two sources, and it creates a number. And this number, just like in the T, the bigger it is, the bigger the treatment effect. And that we can only really interpret it by looking at the p-value in terms of how significant it is. So the p-value in this case, whenever we take the variance between groups and divide by the variance within groups, is 5.3. So the variance between groups is 5.3 times that of the variance within groups. So what does that mean? That means if I have a subject in group 1 and a different subject in group 2, the two things that could cause them to be different are their characteristics like gender, age, exercise, education, and their treatment, because they're in two different treatment groups. And they tend to vary more than subjects within the same group who really have the same treatment classification. So in this case, with this p-value, it's telling me there is some difference in the treatment groups, but all it's telling me is to reject this and conclude that there's a difference in the means somewhere. Unfortunately, ANOVA by itself does not tell me whether or not it's the pharmaceutical group that's different or the behavioral therapy group that's different. It just tells me there's some difference somewhere. So in order to identify which of the groups is different, you have to do post-hoc tests. Or you could compute confidence intervals for the individual differences. So SPSS, for instance, will give you mean differences and confidence intervals and do post-hoc tests for you. So this p-value here, this column of p-values, correspond to the individual pairwise tests that are valid after you've done the ANOVA. And there are different methods for doing post-hoc tests. This is just one called Fisher's LSD, and it's actually pretty liberal, meaning it's more likely to find differences than something like Bonferroni, which you all may be also familiar with. And what this tells me is that both pharmaceutical and behavioral therapy are significantly different from the literature group. Literature versus behavioral therapy had a p-value of 0.015. Literature versus pharmaceutical therapy had a p-value of 0.003. Those are both statistically significant. However, the two therapies are not different from each other. So I can look up here. Behavioral therapy versus pharmaceutical therapy has a p-value of about 0.6. So ANOVA on its own will not tell you where the difference is, but it will tell you if a difference exists, and then you have to go look for it. And I'm going to stop here. We will summarize categorical data, regression, and survival analysis next time. Just to review, today we did inference on means, which concerns a continuous outcome, an interval or a ratio outcome, in 1, 2, or 3 groups. 1 or 2 groups gave us a t-test. More than 2 groups, we did ANOVA. You have to check assumptions before those sampling distributions are valid. Okay? If you have any questions, let me know. Otherwise, I'll see you all next Friday, and we'll pick up with the remainder of the methods.